To discover a mathematical proof using a computer, you have to build an engine that searches through millions of possible logical steps. It explores branches, tests dead ends, and expands its search space exponentially. But building a massive, complex search algorithm introduces an unavoidable engineering reality. Code of that size and complexity will inevitably contain hidden bugs. If the software searching for mathematical truth is itself flawed, we have no reason to trust the final theorem it produces. Mathematical certainty demands absolute, pristine logic, yet the algorithmic process of actually finding that logic relies on messy heuristics, backtracking, and probabilistic guesses. Building a reliable automated prover means we have to stop trying to write perfectly bug-free search code. Instead, we have to isolate the authority of truth entirely from the chaos of discovery. In the late 1970s, a system called LCF introduced a software architecture to enforce this isolation. Today, we call this approach tactical proofing. Tactical proofing divides the theorem prover into two distinct layers. On one side, you have strategic freedom. On the other, you have logical authority. Strategic freedom is the untrusted outer layer. Here, the system is allowed to guess, run unreliable scripts, and execute wildly complex search algorithms to look for an answer. Logical authority is a small, meticulously verified core component that only checks a few basic rules. Everything generated by the outer search layer is forced to pass through this tiny checkpoint. Algorithms can only propose candidate proofs. If a sequence is invalid, the checkpoint rejects it. Only perfectly constructed logic makes it through. Because the code that finds the proof is physically separated from the code that checks the proof, a software bug in your search algorithm can never accidentally certify a false mathematical statement. That rigid checkpoint is known in computer science as the trusted logical kernel. The kernel operates on a strict diet, understanding only foundational rules like modus ponens. It processes proofs sequentially, starting with axioms and stepping forward, checking one deduction at a time to build a verified conclusion. But forward inference poses a severe practical limitation. Humans and algorithms rarely discover complex new mathematics by blindly stacking basic axioms upward and hoping they reach an interesting theorem. The kernel gives us absolute trust, but using strictly forward inference is practically useless for navigating a massive search space. To bridge this gap, engineers use a programming mechanism called a tactic. Tactics reconcile our need to think backward from a goal with the kernel's requirement to check proofs strictly forward. When a tactic executes, it breaks a complex target goal downward into simpler subgoals, but it mathematically guarantees that solving these new subgoals will actually satisfy the original goal. This reverse guarantee is called a validation function. It acts as a continuation pipeline that will eventually stitch the smaller subproofs back together. During search, the untrusted layer runs tactics entirely backward, splitting goals until hitting the bedrock of known axioms. Once reached, validation pipelines trigger simultaneously, running forward to assemble the certified proof from the bottom up. This fully assembled, forward-moving proof object is the only thing handed over to the trusted kernel. A tactic acts as a precise refinement step that carries its own localized guarantee, successfully translating backward human search into forward machine certification. Proving a real-world software system requires executing thousands of these individual tactic steps. A human cannot perform them all manually. To automate the process, we use tacticals. These are higher-order operators that chain individual tactics together into programmable search strategies. Take the then tactical. It dictates that output subgoals from the first tactic feed directly into the second. If a path fails, the or-else tactical gracefully backtracks and tries another route without crashing the prover. By combining sequencing, choice, and repetition, verification engineers construct custom, domain-specific automated search loops that can handle repetitive logic on their own. Tacticals turn theorem proving from a manual chore into an executable programming discipline. They allow us to encode complex human strategy safely into software. Modern systems like Lean and Rock have evolved significantly from early tactical provers. In these environments, mathematical propositions are represented as complex computational types, and the proofs themselves are explicit data structures. A metavariable is an explicit hole in a partially constructed proof term. Modern tactics dynamically generate the precise mathematical data required to fill these holes step by step inside a stateful computational environment. Despite the massive amount of software engineering layered on top, the core architectural rule remains absolute. The fully assembled structure must still pass the hype checking of the tiny foundational kernel. When verifying a secure compiler backend or proving a deep theoretical result like the liquid tensor experiment, the scale of the math changes completely. These massive projects simply cannot be completed by manual human effort alone. They demand an entire ecosystem of heavy, specialized automation. To manage this complexity, engineers mix manual tactic scripts with domain-specific decision procedures and powerful external tools called SMT solvers. These external solvers function as highly efficient, entirely untrusted oracles. They comb through massive libraries of lemmas and propose a pathway to an answer. Once the untrusted oracle provides that path, the local tactic system takes over and mathematically reconstructs the actual proof internally. Tactical architecture makes massive formalizations possible by rigidly localizing trust. You can rely on a completely untrusted external solver because the kernel always independently verifies the final derivation. This same architectural boundary is now allowing computer scientists to integrate deep learning and large language models directly into theorem provers. AI language models have a well-documented flaw. They hallucinate, frequently generating statements that sound confident but are mathematically false. But within a tactical prover, AI hallucination is neutralized. Neural networks sit strictly within the untrusted strategic freedom layer, injecting predicted tactic commands into the search tree. The kernel simply rejects any hallucinated tactic that fails type checking, retaining only the mathematically valid steps. Tactical proving provides the optimal framework for machine-mediated reasoning. It lets us harness the probabilistic power of AI without surrendering our mathematical certainty.